Good afternoon, everyone. It's a pleasure to see an international audience of people from all industries and backgrounds. Good to see you all. I would like to thank you all for registering and taking time out on a Sunday to learn about conducting fire and explosion risk assessment FERA study for oil and gas facilities. My name is Aisha Khalik and I will be your introductory speaker for today. It's a pleasure to host this webinar for you. And as a practice, I would like to reiterate that we are conducting one webinar every month. So please follow us on LinkedIn, YouTube, and make sure to check our website for the latest updates. Today, we have an experienced panel of speakers. I am with my colleagues, Mr. Ijazul Karim Rao, who is Managing Director, Principal Integrity and Safety Consultant. Madam Mubina Khatoon, she is Director, Engineering Services. Mr. Tony William, who is General Manager, Global Sales at Velosi. So before we begin, like usual, we will have a safety moment. Before we begin, although most of us are in the comfort zone of our homes, we should be aware of emergency exits. We should keep a safe distance and generally take care of those who are around us and also of ourselves. So covering the agenda, since this is a quite technical subject, we will touch only the key theoretical and practical aspects of conducting fire and explosion risk assessment FERA study for oil and gas facilities. In this limited 2 hours, we request you to all follow along with us and keep asking questions to help us make this session as engaging as possible. So let's begin. I'll start with Veloci's introduction. I'll give a brief intro and overview of what we do. Velosi is a leading global consultancy firm that provides asset integrity, HSE engineering, and software development services to clients in the oil and gas, energy, power, and petrochemical industries around the world. We also have our in-house proprietary software, Whale Plant, which is an industry-leading SAP certified complete asset integrity solution software, currently being utilized by oil and gas giants such as ADNOC, Dragon Oil, TANUP, BSR, etc. Founded in 1982 in Malaysia, Velosi Group was then acquired by Apple Spain in 2011. With above 43 years of experience, we have expanded our footprints in more than 86 countries so far. And we are offering a full range of specialized consultancy services tailored to the energy industry needs. Here is a map that shows our worldwide existence.
Assalamu alaikum. Good day, everyone. This is afternoon, almost 2:15 here in Abu Dhabi, and I know it's a late evening in the Far East, Malaysia, and morning hours in Europe. So many people are attending in various parts of the globe. Today's topic, it is interesting one, and when we are talking about fire and explosion risk assessment, unfortunately, there have been 2 fires in the refinery fires during first week of October, first week of this month, which means fire and explosion is a real risk for our industry. One fire was in California, in Chevron, and other fire was in Patamina, Dumai. And interestingly, in Dumai, personally, I have done RBI program implementation for Dumai refinery in year 2001. And so this refinery I visited, and when I heard the news about that fire, it went very close to my heart because I had a chance to work in that refinery. So that is the history. It means fire and explosion risk assessment is real, and we need to manage. But however, this webinar is for the beginners. And in almost 2 hours duration, I cannot teach you all about how the FERA should be done, like practically. It requires minimum 3 days training and 2 days on-job training, so as you can practice on the software 5 days. So that is a separate program. But in 2 hours time, like what we'll be spending today, you will have a fair idea like what FERA is all about. FERA, Fire and Explosion Risk Assessment, is a structured and systematic process to identify and assess risks from fire and explosion hazards. The results of this assessment are used to ensure safe facility layout, specify passive and active fire protection requirements, and provide input to EERA, EERA is emergency escape route assessment. ESSA is emergency system survivability analysis. BR is building risk assessment, and QR is quantitative risk assessment studies. It also provides input. And how we do in general, there are three major aspects there. First, identifying if there are any flammable material and which may ignite, and what is the quantity is, and NFPA 30 provide some fair guidelines about that. Then next is how we model into the software, how we do analysis in the software, and that is I'm not promoting any particular software, but since we are using DNV's past and safety software, so we have to explain. Even it is doing promotion for DNV, but that is a great company and they made this software, so we appreciate them. We're using their perpetual license for this modeling. Then once you have output, and this output provides recommendation and mitigation measures, like how we can minimize. See, we cannot eliminate fire and explosion risk. Once you are playing with the hydrocarbons, in hydrocarbons, they can burn, it require three basically things: hydrocarbon, number two, oxygen, which comes from air. So it means hydrocarbons are available, oxygen available, only third angle, which is missing, that is the ignition source. If ignition source comes near to hydrocarbon, once they are released, it can fire, and fire can convert into an explosion. It means this is an real risk for us, and we need to manage it. Now, in normal aspect, why it's important, and how we do it, hazard identification is important. Then assessment, how big is the impact, then how we can reduce the risk, what protection measure we can take, how we can further improve. These all aspects are important. Why fire and explosion risk assessment is important? Two examples I gave in the beginning, one fire in Chevron refinery in California, America, which was during first week of October, and second fire took place in Dumai refinery of Pertamina. That is also another example, a reminder for us, this risk is real for us. Example also, there was, for example, Gulf of Mexico, there was a rig, there was a blowout, and that blowout caused big release of hydrocarbons, and there were 11 casualties were also there. Now, why it caused and how it could be prevented by a good FERA implementation. So there was one aspect was poor well integrity checks. Then there was a poor blowout prevention and maintenance. Then there were gas leakages, and there were ignored signals or alarms by the operators. So what outcome coming from our presentation point of view? A strict application of FERA standard in well integrity checks, blowout prevention, preventer testing, and gas leak monitoring would have prevented the explosion. Embedding these control ensure offshore drilling risk cannot escalate into a catastrophic loss of containment or the effect to the life and the property. Another explosion which took place, which is in China, Taijin, if I'm sorry if the pronunciation is not right, in 2015, where ammonium nitrate and chemical caused massive explosion, killing 170 people were killed, and there was a damage of thousands of buildings. So what were the causes there? Unsafe storage practices, poor segregation of chemical, and ineffective audit. It means FERA also give recommendations there should be proper segregation and storage rules which should be followed, and segregation is also mandatory. And then it should be checked if all the chemical storage handling procedures are being followed and followed strictly. So FERA also provide guidelines with those respects. Piper Alpha is like a famous, or not famous, I would say notorious incident which occurred in North Sea in 1988, which caused the deaths of 167 people, and there was like a full platform was also gone. And as a result, the concept of safety case is also implemented or initiated by HSE UK. And now the safety case identification, safety case SC identification, SC management, performance standard, written scheme of examinations, and then validation, TIV programs, IVB programs, all those are started after that incident. So this was, one can say, game changer, or the management change aspects were brought into, first in the UK, and then the whole world is trying to adopt that safety case management aspect. So in this case, there was a permit to work, like a work permit system was weak. Then isolation, like there was a valve removed, but process was started when there was also weakness in the isolation point of view. And then evacuation system was also weak. So all these aspects could be fairly improved if FERA studies are done and the recommendations are implemented as a serious effort. Now, just to check your presence of mind. So here, there are 4 options, which of the following is a key aspect of fire and explosion risk assessment, because fire and explosion risk assessment does not cover everything. So it may cover estimating project financial cost. It may cover identifying flammable materials and ignition sources. It may cover measuring noise level at the plant. And then it may also have a tracking employees attendance. So please mark your answer, either A, B, C, or D. Then one of them is right. I will be telling that at the next stage. Please put in the question answer session. People are marking the answer. Okay. So I can see the screen. Okay, mostly right. Mostly right. So answer is B. So FERA does not do financial aspect. FERA does not cover environmental aspect. It also does not cover employees attendance. It's say identifying flammable materials and ignition sources, because these are 2 things which we need to manage. Air is anyway available, which can help always in oxidation process. Now, just is a repetition little bit, but the people who are new in our series of webinars, because we have covered before QRA, then we covered BRA, it was our last webinar, and also we have covered ERA, ESSA. So there are some repetition. So I will be going through the same repetition process today, just to make sure you understand the concept of risk assessment, because most of you or some of you could be new attendees as well. So what is risk analysis? Basically, risk analysis is we identify the hazard and the hazard probability of occurrence, the likelihood. And then if some hazard occurs, what would be the consequence? The consequence assessment. And then multiple of probability of failure into consequence of failure gives us risk. So risk, aspects point of view, risk sometimes is imaginary, sometimes it could be also a number. It could be a number, it could be imagination. For example, if we are crossing a road, so we know that if we don't follow the signal, and if accident happens, it could be fatal. The consequence is very high. But probability wise, so we follow the safety rules, signals, and the road safety aspects. Then accordingly, we try to minimize the probability. It means sometimes consequences are high, but we try to minimize the occurrence, possibility of occurrence, or probability of occurrence, or likelihood of occurrence. Same in in refineries, in hydrocarbon installation, petrochemical plants, even a nuclear plant. So what do? We know that if accident will occur, this will be a big fire, as the 2 fires we have seen during first week of this month. So, but those refineries are working from years. There was no incident, but all of a sudden there is an incident and cause big effect on the assets and the people. So the point is, we need to minimize the probability of occurrence at design stage, at project stage. We try to proper designing, inherent safe design, proper layouts, proper control during construction, proper control during procurement process. of the various vendor items, then installation point of view, pre-commissioning, commissioning, mechanical completion, electrical completion, instrumentation completion, all those aspects we try to cover so properly, so as when we operate the plant, the risk of fire is minimum or near to like as low as it will never occur, like 10 to the minus 9. But risk is still there and it has to be assessed. So risk can be assessed by two methods. One is qualitative, which is mostly judgmental, and other is quantitative, which goes with the numbers, like probability of failure calculation, also calculated by numbers, frequency, and so effects, and then consequence also quantified, like we do in QRA, we do in FERA as well, and BRA as well. So how this history of risk analysis started? This is like what we see happening after World War II. The concept of the risk assessment came into picture. In 1950s, companies turned to risk management as an alternative to the extensive insurance, focusing on protecting against pure risks. Then 1970 to 1980, companies adopted financial derivative as a key instrument to strengthen and expand risk management practices. 1980s onward, the formal risk assessment standards, practices, softwares, all were adopted by the industry, and now it is a part and parcel of every design aspect of the plant. So benefit, see, once we like element-wise, there are three elements in the risk, as I said earlier. One is the probability of failure. First, identification of hazard. Then, what could be the probability of occurrence? What could be the quantification of the effect, consequences? Then, if you multiply both in quantitative risk assessment, we can understand the concept of risk. And like in some time, we try to minimize the consequences. Sometimes we try to minimize the risk by taking the preventive measures. And in this way, risk analysis gives us the steps like what are the causes, how the cause could be minimized or neutralized or completely removed. Consequence-wise, how we can minimize, for example, having lesser inventories, proper segregation, and so and so. So the benefit of risk assessment is once we know what may go worst, if we try to focus on the areas of the probability of side or the consequence side, then it can give us better risk management approaches. And if we can manage the risk, it means the probability of fire could be eliminated and effect of the fire could also be minimized if fire occurs. So these are the general benefit in the risk analysis. Now, like how we do it in general, in risk, what I said earlier also, we have identifying the hazards, consequences, and risk is the first step. Then analyze the risk, like what is the driver of the risk, as I said earlier, whether hazard side or consequence side. Risk is a multiple, so there's no risk-wise we can scale up or scale down. Like if the items are high critical, medium critical, or low critical, or high risk, or very high risk, medium risk, low risk, or negligible risk, there could be a various categories. Then analyze those risks, focus on their drivers, and accordingly see that how those drivers could be controlled. Then based on those drivers, we try to develop risk management plan. Then implement risk management plan on the actual practice and monitoring of the those management aspects. Let's say if we have alarm management system in the industry, right, in the plant, if we know that if any deviation will be there in the process parameter, there would be an alarm. And if that alarm would not be attended by the operator, there could be next step either trip, interlock may act, or there could be an accident on the plant. So we know that what is the process safety effect of that alarm, what is the process safety time for the operator to act, and what he has to do. In this way, we can monitor and manage that particular risk, as example I just gave you. Now, in general terms, to understand the concept of the risk, like first the system definition, then hazard identification. System definition means what process we are running. And sometimes, like if it is a hydrocarbon, non-hydrocarbon, toxic, no toxic, and explosion may possible, fire may occur, and so and so. Then hazard identification, their consequence calculations in terms of dollar, in terms of fatalities, or in terms of effect on the environment. Then likelihood, multiple of those gives you a risk. Right. This is the risk concept. Now, just try to see like how an insurance company is using risk calculation as one of their decision making tool. For example, one insurance company is, let's say, insures like 1,000 cars, and they're charging, let's say, USD 1,500 per year per car. And if you see total revenue, what they're getting is $1.5 million. Now, if everything goes as per their calculation, 50 cars, let's say out of 1,000 cars are getting full accident, and they end up paying like price for each car, let's say $15,000, and they will be paying 750, which is less than or half of the 1.5 million. But let's say if this number goes double or more than 100, then insurance company would be in loss. In this way, you can imagine what is the effect of the basically risk in terms of number, like what premium insurance company should charge per car, average, and similarly, if there would be maximum number of incident as per the previous track record of the last 10 or 20 years, they can say, okay, this has been the trend. If there's no hurricane, there's no weather abnormality, it would be safe for the insurance company to run their business. So this is the understanding or demonstration of the risk in terms of the numbers. Right. Now, we earlier also I discussed about there are two kinds of the risk assessment. One is the qualitative risk assessment, and another is the quantitative risk assessment. Qualitative is mostly judgmental. For example, we can use normal risk metrics. We can use any scale, and then accordingly, by combining a team of people, we can say what would be the probability of this occurrence, then what would be the consequence of this occurrence, then accordingly risk is assessed, which is normally opinion based. But the quantitative is done by using certain numbers. Like the previous example of the car insurance company, that is a quantitative number, because we have the price of the car, we have the premium to be paid, like the price of the car, what we need to pay to the owner of the car in case there is accident happens, and similarly the number of cars being insured, but it is being quantified based on the previous 10 years, 20 years history of that particular country or that particular city, and then accordingly we can assess that. So the quantitative risk assessment is mainly driven by the numbers. Qualitative is driven by the judgment. And sometimes there's also in between semi-quantitative risk analysis. One is qualitative risk assessment, second is the quantitative risk assessment, and sometimes there could also be semi-quantitative risk assessment, a half number, half judgment, or some number, some judgment. So all three approaches are available in the market, and those are being used for the risk assessment, because sometimes it is not easy to quantify risk always in numbers, because sometimes information may not be available. So we use in that scenario semi-quantitative. So in quantitative risk assessment in general, there are like four studies, or like I would say three studies are there what we are using: QRA, BRA, and FERA. QRA, FERA, and BRA. Output of these three studies is utilized under ESSA and EERA. ESSA is Emergency System Survivability Assessment, and EERA is Evacuation, Escape, and Rescue Analysis. These two studies are basically subpart of QRA and FERA. Now, we are discussing three studies: BRA, QRA, FERA. BRA is Building Risk Assessment, QRA is Quantitative Risk Assessment, and then FERA is a Fire and Explosion Risk Assessment. So, we need to understand what we're talking about. Why these three studies are done? If in all three studies, we are using fast and sweaty software to DNV, and same model, but with some input parameters are changed a little bit, and then output receptors or the assessment aspects are changed. And the same model is used to execute all three studies like in series. We don't do in parallel because the same model is utilized with a little bit of adjustment. So what is BRA? BRA evaluate risk to people in occupied building from a fire, explosion, or toxic release. Like BRA is focused, there is a control room, there is admin building, there could be a workshop in a plant area. If there would be any fire and explosion in the plant, whether it would affect the people sitting in those buildings. This is BRA. Whereas FERA is focused study of the fire and explosion hazard and their impact. So if fire and explosion also reaching to basically the control room, to workshop, to admin building, or in any neighboring facility. So it means FERA and BRA are correlated, but only thing in BRA focus is only mainly on the building, but result from where it will be coming? It will be coming from FERA. If there will be explosion, if explosion will affect the nearby building, if there would be a fire or release of hydrocarbon, it will reach to the nearby building. Same is the QRA. QRA quantifies likelihood and consequence, in both. Where BRA is there, FERA is there. Same in QRA of hazardous event using measurable data. Same measurable data is being used in all three. But the impact is here we try to see risk aspects in the facilities. Here we see fire and explosion hazards and their risks. So definition point of view is like a little bit confusing, but process is same, objectives are same, a little bit different. Here focus is on the nearby buildings or control rooms. Here risk in the facility. Here focus is mainly on the fire and explosion hazard purpose. Purpose of the BRA to protect building occupants and recommend mitigation, like if the people in the nearby buildings would be safe, if the people sitting in the control room would be safe. Here, to demonstrate facility, safety support, alarm, and cost-effective safety decisions. Here, to identify, minimize fire and explosion hazards, ensure risks are within alarm region. Then scope. It is basically narrow. Building occupants, the focus is mainly on the building occupants. It is the broad, entire facility and operation. Broad. QR is more broader. Whereas FERA is also medium. Fire explosion risk affecting assets and people. Then the relationship may use QRA as a final stage, can integrate FERA input as well. Used independently or within BRA and FERA. Three are like the studies are interrelated. Provide hazard data feeding into BRA and QRA. Like first of all, like we are used to do. First, we try to do FERA. Then we use the same model to do QRA. And then part of QRA, we try to do BRA in this way. Like time zone also, like when we are estimating man hours for like a bidding purpose. So we take full like a man hours for FERA, almost half of that in QRA and quarter of that for BRA, like that. This also can give you the nature of efforts, like isolatable sections, parts count, inventory calculations, plant layout and facilities, all are covered under FERA, but same information is being used in QRA with some modifications here and there. Next, the process, like all three stages are there. Hazard identification, consequence modeling is there in BRA as well, QRA as well as FERA. Then detailed QRA, if needed, is done or may not be done. This depends. Then here, comparing against acceptance criteria, what is the risk? Basically, here, risk evaluation in terms of fire and explosion modeling outputs. BRA reports with hazard occupancy data, then safety recommendations, numerical risk values, risk contours map, and alarm justification. Here, fire protection, safe layout, mitigation measures. Then application, like assess safety of occupied building, compliance with API 752. Then use across facility life cycle to justify safety decisions and with an acceptable IRP IRPA risk. Then basis for fire explosion protection system, support BRA and QRA. So this is just to give an idea. So when we talk about BRA, QRA, FERA, so these are interrelated and same information, same model can be used, but with a little bit focus on the different outputs. Quantitative, so as everybody is not sleeping, so just I'm asking question to the participants, like if you are active and everybody's like listening what being presented here. So in quantitative risk assessment, overall risk is calculated using which of the following formula? One of them is correct. So people started writing also already. mostly are correct. The answer is C, PUF into CUF. It is not PUF plus CUF. It is not PUF divided by CUF. It is not PUF minus CUF. The risk is multiple of PUF and CUF. This is true for the basically quantitative risk assessment. And in qualitative risk assessment, correlation is used. That has to be understood. In qualitative, it cannot be multiplied if you don't have a number. So that is the correlation between PUF and CUF. And then we check the basically risk position. Standards and regulations. So there are a whole lot of standards available, but like my objective is to, when you give you the number, you are familiar, okay, these are the standards. Like if you need to carry out any study, so you can get some or all of those standards, so it can help you to get prepared. Like when we say risk assessment is ISO IEC 3100, 31010, year could be any. Then alarm guidance 2013 and 2014, guidelines are available. NFPA 101, live safety code, requirement for building safety, fire protection, and safe egress. Then NFPA 30 is a very famous standard. We talk flammable and combustible liquids, like how those liquids should be managed. Then management of hazards associated with the location of process plant, permanent building is API RP 752. Then similarly, there's ISO 15544. There is a API RP 14J, API RP 14C, API RP 750, then ISO 31000, like risk management guideline principles and framework for systematic risk management. Here, not like still list going on. There is a Safety is a DNV is like a guideline. Then there is also yellow book, purple book, and then fireproofing practices as per API RP 2218. So PGS2 and PGS3, these are the famous, like we remember always yellow book and purple book. Those are available. Fireproofing point of view, this is one of the outcome of the FERA. So API RP is very, very important. If I have to say you, like here, some important, NFPA 30 is more important, right? Then alarm guideline is important. When regarding BRA, 752 is important. But normal risk concept is 750. This is important. So some standards are important, some can be used as a supporting document. So just to get you some picture, so I will not go through the content, but like this is the front page and the content list for IEC 31010, risk management, risk assessment techniques, qualitative, semi-quantitative, and quantitative. These techniques are available. Similarly, alarm framework, this guideline is available, guidance on achievement of alarm in the process industries, because we cannot bring risk to zero. Risk would be there, but it should be as low as reasonably practicable. So to understand the concept of the risk and how we can manage, the concept of alarm framework is very important to understand that concept. NFPA 101, life safety code. This is one of the important standard, and it can be used as a general reference. Then NFPA 30, flammable and combustible liquid code, how we should manage them. A big risk, this is a big content list. This is one of the key standard of NFPA, because hydrocarbon or any process industry we are running our storage, so NFPA 30 provide very important guideline regarding safety data sheets, their diamond, their risk reactivity, oxidation aspects, and so on. So this standard is very, very important for you to keep nearby. Then RP 752, which is basically for the building safety. Then this ISO 15544, which is basically oil and gas offshore production installation requirement and guidance for emergency response, ERP. This is ERP, emergency response plan, in case a fire occurs, how to behave, how to react, whether organization, whether the leadership would be ready to take control on the situation. Then API 14J, it is a recommended practice for design and hazard analysis of offshore production facilities. Then 14C, analysis, design, installation, and testing of safety systems for offshore production facilities. Then management of process has its normal like risk management aspects, risk identification, risk assessment, and management aspect, general guideline. Then this is a risk management guideline, how we do risk management, like how we can control probability, how we can control consequence, how risk could be minimized, general guidelines. It will not give solution for everything, like what kind of aspects we can apply, how we can operate like our facilities within a LRF region. Then this is the severity 7.2. This is a new version. I think 19.9.7 even there. So our slide is old, and now it's not DNV GL anymore. It's DNV. So my slide is older. So now GL is finished. DNV standing alone. Here, this is the yellow book. This is the content, and this is the purple book. It's very famous in the guidance for the quantitative risk assessment. And first one is the method of calculating physical effects of any hazard. Then like API 2218, which is basically fireproofing practice in petroleum and petrochemical process plants. For example, if there would be any jet fire or pool fire, what fire rating should be there? Like the structure should not collapse, concrete building should not collapse. So with those aspects, like what kind of fireproofing, for example, cemented base fireproofing or mastic material based fireproofing up to first level of the like a pipe rack, or up to the full jacket of the like full skirt of the pressure vessel, or like other leg support of the vessel, which should be fireproof. The fireproofing normal requirements are identified in API RP 2218 standard. So here, since we are based in Abu Dhabi, so most of the studies, we are working in the whole region, but since the protocol which is being used by ADNOC, so we appreciate, since we are working with like Saudi Aramco, Qatar Petroleum, OQ or KJ or KOC, all the Middle East countries. So the protocol, what we see being followed by ADNOC is one of the most robust one. They have a standards to carry out all the full, let's say, pattern of the various HSE studies and COMAH, control of major accidental hazard. Nowadays it's being called SCEs, identification, and so on. So there are various standards. For example, HSERM, no, they're being changed to control practices. The new standards of ADNOC are coming. Maybe next webinar we will use those new standards. These were the practices. No, standards are being renamed as practices, but these are the old standards. Like ST09 is basically for FERA, and ST10 is for QRA. ST02 is a basically general HSEIA standard. Then ST06 is how to prepare COMAH, which would be safety case in future. Then ST07 is EERA standard. Then ST01 ADNOC HSE risk management standard. Then ST08 ADNOC emergency system survivability assessment standard ESSA. And then also ADNOC CFD dispersion and explosion modeling standard is ST14. So similarly, these are the front pages of those standards, and this one is for FERA, this is for QRA, this is for HSEIA general, this is for COMAH, this is for EERA, emergency escape route analysis. Then here is HSE risk management guideline overall. Then ESSA, emergency system survivability analysis. So in this way, ADNOC has helped a lot. We feel very much guided and appreciated, because we don't need to go to the other international standard while working with ADNOC. But in other countries, like if we are doing the similar services for Qatar Petroleum and for Saudi Aramco, so they have also standard guideline, but not up to that extent as ADNOC has produced. So this way ADNOC is helping in the region to other companies also to follow the ADNOC approach. Then CFD dispersion modeling, which is the ST014. So now I will start with the FERA case study. And in this study, I will, last stage, we will have a question answers, right? We know that it could be a boring little bit in between, so we have few questions in between. So as we go through the case study, so I will be presenting the first part, and the second part, like output and results, would be presented by Ms. Harim. She is a practitioner like FERA and QRA studies. So she would be able to explain FERA output better than me. So I would go to the earlier part, and last part she will present. Okay. Here, like we can, in some areas it is called safety case, and here is HSEIA study scope. So Velosi was like contracted by a company. I cannot say, I don't know, companies that ADNOC standards are there. But what we have done, not to reflect actual result, we have mixed up various facilities, and the various like input is taken from A project and output is taken from the B project. So as you cannot correlate like what the results are. So this is to protect the sensitivity of the data. So we have mixed up the various studies and also mixed up the data or changed the data also. So any result what you will see will not be able to reflecting any particular asset of the ADNOC. So it is a mix up. So that is like to protect the rights, copyrights of ADNOC. So only thing is approach point of view, since we are presenting based on ADNOC standards, so you perceive that the study is for ADNOC, but it's a mix up. This is very important for us to clarify. So otherwise it can misguide, or it may say, okay, oh, why this kind of number or that kind of number. So numbers are also changed, and the symbolic number. This is my big caveat and qualification, sir. Here, objective of HSEIA studies, the safety case studies, normally what we carry out, the compliance with HSE regulation and standard of ADNOC, major accident prevention aspects plan, then also health, safety, environmental hazard identification and their assessed, the risk managed with suitable measures and critical equipment in place, then on-site and off-site emergency plan established, then risk reduced to alarms, safeguarding life, property, environment, and business. These are the 6 objectives of any HSEIA study or safety case. Now, there are various deliverables. For example, hazard invid OID workshop report, BOTI workshop and report, HECS SC register and performance standards, update of integrated QRA, then fire and explosion risk assessment, which is also part of all those studies, then emergency system survivability assessment study report, escape evacuation and rescue assessment report, toxic gas dispersion modeling report, control of major accidental hazard report, review of existing company HSEMS system, then environmental impact assessment report, occupational health review and assessment report, then HSEIA dossier. Here, like what we are covering, the current FERA study scope is limited to update the existing like a FERA report based on the gap analysis conducted as a part of current HSEIA. The battery limit of the facility studies as part of FERA are gas system, gas plant, sulfur station, and pipelines. See here, under FERA study objective, we have to identify the accidental loads, adequacy of fire protection system, and risk reduction recommendations. 3 major aspects what we are going to cover under this study. Now, again, to keep you awake, there's one question. What is the full form of HSEIA? First is health, safety, environment impact assessment. Second is hazard, safety, environment and inspection audit, health, safety, emergency incident analysis, human safety and environmental impact audit. So there are answers coming. Good, mostly are right, and answer is A. So this question we added so as we can engage you during the discussion. Otherwise, people may sleep because it's a lengthy presentation and like sometimes boring also. So FERA study deliverables. FERA, like we said, HSEIA, there are various deliverables, but in FERA also, there are deliverables, like a detailed one. Core deliverables, for example, frequency of overpressure levels, frequency of thermal radiation levels, identification of loss of containment scenarios, consequence modeling results, recommended additional safety measures for further risk reduction, fire and explosion risk reduction measures, and detailed deliverable also add further like engineering consideration, as a recommendation given by FERA study. Safeguard selection if we need to identify and add. Then basis of design documents, compliance documentation, input for other risk studies like BRA and QRA, ESSA and EERA. Basic data requirement. The basic data normally what we need is like PFDs with heat and material balance, P&IDs, then plant layout, 3D model. So once we do that, so we need to identify isolatable sections. So for isolatable section, we need to calculate inventories, their compositions, and operating conditions, and that calculation is required. Then we also need what kind of safety system, for example, existing, or if we're designing or their existing system, what kind of fire and gas detection system is there, what kind of emergency shutdown system is there, what kind of active fire protection system is there, and what kind of passive fire protection is there. Then while we are modeling the system, like parts count, then frequency calculations, the likelihood calculation, then ignition probabilities, and equipment failure rate, if it could be plant specific, or it could be taken from the URIDA or the similar other aspects. Then consequent data, what we have taken from the inventory side, there could be a thermal, radiation, and fire aspects, as well as there could be escalation scenarios, and plus there could be also toxic elements within the process, which could also be effect like having other effects like H2S and SO2 or other like ammonia. Those aspects are also considered. Then environmental and meteorological data like wind speed, direction, temperature, and stability class for dispersion and fire modeling is also important. So all that data we normally take for the modeling aspect. This is easy to explain, but when we go in detail, like as I said earlier, like as we do it, it's not difficult. We have trained many people and they're working in the field, but same time, it cannot be done without supervision and without supervision of a trained and experienced team, right? And then at lower side, there are various parts of the activities which could be done by junior people. Modeler, it should be very experienced. Then reality check should be done more experienced and the team. So this way we try to do FERA, QRA, and BRA. Here, like just to understand, like when we are doing, we should know what the facility is. Like first thing, as when we are going to do FERA, QRA, or BRA, what is the process plant? What kind of service is there? It's a hydrocarbon with H2S. It could be an ammonia plant. In ammonia, first of all, we are bringing in methane. We are preparing CO2, and also we are taking nitrogen from, and the CO2 nitrogen being combined to make urea, and so and so. So in this way, as we understand the process, whether a chemical plant or whether it is a hydrocarbon plant or refinery, we should know the process and their units so as we can imagine what impacts there could be. First of all, there should be a normal hazard identification and people should know what can go wrong. Then accordingly, we're going to quantify them by the use of software. So the first thing is we should remember, we should understand what the process conditions are, what process is being done by that particular facility, what is input, what is output, what kind of reactors are there inside, exothermic reactor or endothermic reactor, then accordingly effects would be there. Like the fire which occurred in Chevron, that was in one of the SMX unit, which is exothermic reactor, and there is a probability of fire if temperature goes out of control because exothermic. That is very important to maintain the cooling system or safe shutdown of the facility if there is any abnormal situation. So it is very important we understand the process of the facilities, the composition of the facilities, and the sensitivity or the reactivity of those chemicals which would be released in case of any leakage or rupture occur in the plant. And then what kind of ignition sources are there, whether hazard area classification done, whether ATEX compliance is done, whether like a heater and the process plant distances, there if any fired heater is there in the process facility, whether those are kept at a safe distances. And then we also see if like a process plant point of view, we have a mind like how far is the control room, how far is the admin building, if the exits routes are not impaired by any kind of like a leak, rupture, thermal effects, and so and so. Here, so as I said, you will see mix and match. So it's not like the facility is different and the layout is different. So this is intentionally changed. You see a project location map, which may not be matching with the previous description. This is change is done intentionally. But anyway, it is showing you how the process facilities are placed, and we take that as a project location map for the input into the software. Fair approach. Like, so my part is approach part, result part would be presented by Harim. So here, FERA methodology and assessment register, assumption register, sorry. Methodology and assumption register, that is the first thing we do. Then selection of failure case scenarios or isolatable sections we mark. Then we also say physical parameters selection and inventory calculations. Then frequency assessment, but we take that whole size, failure frequency assessment, ignition probabilities, event frequency assessment. Then, like here, consequence side, source term modeling, physical modeling effects, then impairment criteria, consequence impact assessment. If you see this, like it looks like there are many calculations since we are doing QRF around every day. So I see them, step one, take the PFDs and PNIDs, mark isolatable section, or in RBA we say inventory groups. The inventory group is like if there would be any leakage or rupture in a particular section of the plant, whether the whole inventory of the plant will go into that leakage route, or there would be only a area within the basically ESD systems. Like if there is an emergency at the plant, there is a leakage, then we will trip the plant, the inlet will close, outlet will close, BDV, blow down valve will open to flare, and ESD will shut down. So in that area, there is a limited inventory which will go out in the leakage side. And this, like a probability of happening, is being done like what is the, how many flange connections are there? What is the diameter of the pipe? What could be the possible hole? Like normally, we are considering like a 4 or 5 scenarios. For example, 5 mm hole, 25 mm hole, 100 mm hole or full rupture. And similarly, inventory is coming from the isolatable sections. But if we try to do it, like practically it's not so difficult, but if we try to understand from this presentation, then it would be nearly impossible to handle it. But this gave you an idea how the FERA is being done. Or the same approach up to these two parts are same in QRA, same in BRA. Then do fire and explosion risk calculations by using the software. Then accidents curve feasibility, like where the impact would be. Identification of volume blockage ratio, BBR, and blast strength curve. Then determination of the potential explosion sites, PES. Like if we want to take a platform or a structure or a building nearby, so we mark them as a PES, potential explosion site, and then accordingly we see the effects on those particular nearby receptors, right? Then active pacifier protection system, adequacy check, requirements. Then fire and explosion risk assessment, correct? Like a FERA workshop is also done once we have the result, right? Then conclusion and recommendation. So here, these are the steps what we normally do. Here, the same steps. I'm wasting your time, but I'm repeating so as if somebody is trying to take this presentation more than like they want to use this for actual working they can do. So first, hazard identification. Normally, it is coming from hazard workshop. So failure cause scenario, like a cause scenario, this would be modeled by software, but we have to take isolatable sections. The people who are familiar with RBI, they take it inventory groups as in accordance with API 581. These isolatable sections in QRA and inventory group in RBI risk-based inspection assessment is more or less same. Consequence assessment, this is done by the software. Frequency analysis, this is done first outside, like by parts count, by taking the frequency of that particular object type, and that is fed into the software. Similarly, we also add like a probability of ignition, like if there is, for example, firefighting, fire and gas detection system, ATEX compliance with all electrical instrumentation items, and all the heat or hot spots in the plant are managed. And then we do fire and explosion risk assessment, accidents curve feasibility, and then we say that after accidents, like what kind of active and passive fire protection system is there. If we need to improve that, then fire and explosion risk assessment workshop is done to see that everything is within a LAR region. Now, if we see like a normal pattern in HSEIA or safety case. So data collection is the first. We do hazard workshop, we do inward workshop, and we're doing OHED workshop. And then hazards are classified. There are MAH, when fatalities, one or more fatalities, that goes to an MAH, major accidental hazard, and then significant environmental impacts. And non-MAH or non-significant environmental impacts, those are covered by HSCMS procedures. Here we need to have more detailed studies. Those more detailed studies, EMP and WMP, then modeling studies, QRA, FERA, EERA, BRA, then drilling, cutting, and dispersion. Like here, we need to convert like those studies to a COMAH report and then overall HSEIA report. So same aspect, little bit more details, like we have like OHED, inward hazard, same workshop, classified same, which is studies mean either ORA, EIA, air and noise monitoring, QRA, FERA, SIMO, MOPO, BRA, ESSA, these studies, this could be shown sometime this way also. And another way of control of major accidental hazards, like I don't want to confuse all of you, but here, like if I go back, OHED inward hazard workshop, only workshop. And this will classify MAH, non-MAH. Two things done, two things only, easy. Then non-MAH and insignificant environmental impacts would be covered by HSCMS procedural. But MAH and significant environmental impact would require various HSC studies, which are being done. All this. And then it goes to the COMAH report. Okay, sir. Now, under COMAH report, this COMAH report, where everything is combined, so that is coming here, control of major accidental COMAH report, major accidental hazard, MAH identification done by hazard workshop. Then major accidental hazard MAH assessment is being done by these studies, all QRA, BRA, FERA, ESSA, EERA, and H2S zoning studies. This is done. Now, then in MAH, we also do BOTI. Under BOTI, we make HECCS or FT register and performance standard, which is done for feed stage separate, EPC stage separate, operation stage separate, and HEC critical register is activity and registers are identified. Then all these risks are there. Then we see alarm demonstration. Like whatever activities would be there, like a process would be there, the risk would be as low as reasonably practicable. And then last part of COMAH is emergency response plan, which is prepared. Drills are also conducted as per those guidelines and procedures. This is very important. So this way, we see that how the COMAH, or we call it safety case. I think next standard under control practice, this COMAH report would be called as safety case. Like we ensure that the plant would be managed safely and we would have a proper system in place to minimize all the MAHs which could be potentially take place. Our approach is same, basically. Is not like approach is same what we just explained, but only thing is we say actual case now. Actual case. Here, building and like hazard identification. Here we carry out hazard identification workshop where term of reference is prepared, then pre-populated hazard worksheet is prepared, then hazard workshop session is done, and then we prepare the hazard workshop report. Here, for example, hazard related to basically safety, inward hazards related to environment, OHED hazards related to health. Those are done, and MAH, like a major accidental hazards in terms of safety, like one or more fatalities, those are identified. Then identified hazards impacts are related based on ADNOC risk matrix and ADNOC risk management standard. These are to be matched. Here we change the numbers, but we're showing how many like high hazards in this particular facility, what we're referring, not there. OHED wise there are 20, but otherwise not high risk hazard. Then there are high medium risk hazards 5 and 3 and 123 in the health side. And the medium risk hazard 93 and 36, low risk hazard 19 and 38. Number of recommendation given for each kind of hazard 17, 11 and 26 by the workshop attendance. Here, this is the sample worksheet where we try to see the hazards. For example, we node by node, what are the threat, top event, consequences. Then there's a potential risk, preventive control measures, and then mitigative recommendations, then accordingly residual risk, and this is the action and recommendation as a result of that worksheet we prepare. So this is the one sample, and there is not only one sheet, there are like many sheets. Then like a major accidental hazard which comes out of the hazard like a workshop, and these are few examples we are showing you here, like if the gas H2S, which is 22.8 mole percent and 241 bar pressure, then flare system H2S 22.8%, then downstream of FIPS, transfer line including pig launcher receiver. So these are the example of those hazards like MA 01 to 08, and top event is release of hydrocarbon from flare due to loss of ignition, release of propane from cylinders, release of hydrocarbons again, and so and so. Now here, like major accident event, what can happen? We have to imagine. So as we know that those are the major fires. Remember, there would be a question also next. I'm just telling you as a guess. This is the like jet fire, pool fire, vapor cloud explosion, dust explosion. These are the four kind of fire and explosion can take place at the facility. One is jet fire, mean fire driven by the gas release, and then flash fire, and then jet fire. Then pool fire is a like dike or the tank fire. Then there could be a liquid which could be fire. Then it is a vapor cloud explosion. If there is a first release of the hydrocarbon for a certain period, all of a sudden there is a fire which can turn into an explosion. This explosion could take place, for example, in server handling area or anywhere where dust is available, that may also explode like this picture. Now, isolatable sections, like how we mark isolatable section on the PNIDs. The isolatable section we mark within the emergency shutdown valve, emergency depressurization valve or blowdown valve, the remotely operated valve. Sometimes people say we should take motorized valve, or people say we should not. Then normally and lock closed valve, like a fail-safe actions, if the control valve which are fail-safe closed, then those could also be considered as an isolatable section. The total are, like in this facility, 200 isolatable sections are identified. The number is changed, but I'm just giving a number. Here, like various isolatable sections, boundary, start, end, temperature, pressure, flow, stream number, composition ID used in fast software, and H2S percentage also. The percentage also you will see different than earlier number. So because the numbers are changed, we are not showing the same case. So here, the whatever input data you see different, basically spreadsheet. These are to save the like sensitivity of the information. So we are not showing exact, it is a matched and mixed. So here how we mark the isolatable section from one ESD to other ESD. You can see that one ESD to this ESD. This is the complete one isolatable section. If it is purple color, other isolation section, and so on. So this way, these isolatable sections are marked on each PNID. Then parts count methodology, like this example we are showing here, like all the flange connections. For example, flange connection on the vessel, this flange, this valve, if they're flange, if they're welded, will not take. Only flange connections where leak can occur. Other places, we take potential hole in the pipe or equipment, there's separate criteria. So flanges, manual valves, actuated valve, their flanges are counted mainly. Or the manual and actuated valve, they're like their trim or their actuator may also leak. So that's the one potential leak point. Then instrument connections, if they are like transmitters, they may also leak. Then release frequency is calculated as a combination, and piping length is taken more than 2 inch as per the isometrics, basically, drawings. Here, leak size distribution, like if the presented leak size, like generally 2 inch, 2 mm, 5 mm, 10 mm, 100 mm, this is the range, but we take this as a representative leak point. Representative leak size, if we take, for example, for small leaks, 5 mm or 10 mm, medium leak, 25 mm or 50 mm, large leak, 100, and there is a rupture or the full bore rupture can take. So these are modeled in the software, and these features are already available in fast and sweaty software. Then input sheet sourcing thermal modeling, like here, for each isolatable section, we have to identify it is the operating conditions, like a composition, toxic element composition, and also the density, volume, and mass. The rest of the information will be taken by the software itself. Here, inventory calculations like both static as well as the dynamic. And then also conditions are taken into consideration. For example, if automated ESD and blowdown system is there, then the system would be isolated within 2 minutes. Manual ESD and blowdown, it will take 5 minutes for operator to act. Then accordingly, we have a static inventory, discharge rate into detection and isolatable section of the valves. This is the dynamic. The total mass inventory is static plus dynamic inventory. Then inventory calculation wise, so we like static and dynamic inventory shall be calculated to identify and assess the physical effects from all the isolatable section with different leak sizes as per TNO purple book. Following leak sizes shall be used for dynamic inventory calculation: small 5 mm, medium 25 mm, and 100 mm. So this is like how we calculate, and so this is the main time consuming activity in QRA, VRA, and FERA, because we have to mark all isolatable section, we need to calculate all the parts count, and we have to make all these calculations, and then your input is ready for the software. So this is the most time-taking activity. If these calculations are done rightly, then we would have a more reliable results. Failure frequency calculations, basically there are generic failure frequencies, then we have to multiply with these all like a potential leak points like a phalanges and valves, their trims, their actuators, and then accordingly we calculate what is the resultant failure frequency for any particular isolatable section. So example of failure frequency, for example, for like a 3 to 10 mm, 5 mm, these are the basically isolatable sections we have calculated. Then for 25 mm, these are calculated. Then 50 to 100, under 50, these frequencies are calculated. All these frequencies are calculated isolatable section by isolatable section, taking generic, then multiply with the resultant of the potential leak point like flanges and valves. Then assessment like what is the contribution coming. For example, if you see here, small leaks 5 mm, medium leak 10 mm, large 100 mm, full bore rupture. So if you see this is a contribution, in this particular case, there is no full bore rupture, but here some are there, right? Now, if you see other side, a failure frequency in the gas plant. So here large leak is there, and like a full bore rupture is also there right here. So these are the representation of the various frequencies which are applicable on each isolatable section, gas plant wise. Here now, from FERA modeling, following results would be extracted from FAST software. Now, we're going to consequence the result assessment criteria. This is also very important. For example, from FERA modeling, following results will be extracted from FAST software: jet fire 37.5 kilowatt per meter square, 12.5 kilowatt per meter square, and 4 kilowatt. Now it's becoming more technical. So people who are not in practice, it would be difficult to imagine. Up to now, things are doable. Now, these are the input data we model into the software, and then software give us the result. Flash fire, lower flammable limits, and half like a low flammable limit. Then vapor cloud explosion, multi energy and BST obstruction method is used. Vulnerability assessment for human and plant and structure shall be defined from OGP 434, which is 14 into 15 standards. This standard we use. Very important, the people who would be doing the job practically. Then, from FERA modeling, following results would be extracted from the SFETI software: location-specific risk, LSIR, land use planning criteria. Then individual risk per annum, IRPA, which is very important, risk tolerable criteria. Then societal risk, curve outside the boundary of the project, like a societal criteria. These are the three major ones. Then ALARP wise, we know the region wise maximum tolerable, this one, ALARP or tolerability region. Like if risk is within this region, it is still considered acceptable. Though acceptable region is low, below here. Like this is maximum tolerable limit 1 into like 1 in 100 years, 1 in like per year, 1 in 100,000 per year, and this one is 1 in 1,000 per year. Then here the maximum tolerable limit 1 in 10,000 per year. So there are various regions are there. Then according to high risk ranking must be reduced up to a large level. Medium risk ranking, a large demonstration is required and sensitivity cases can be introduced. Low risk ranking, tolerable risk, no further risk reduction measures are required. If risk is coming under this green region, no issue. If this one, we try to bring lower side, and if any risk is coming under red, plant cannot be operated. So this is like a societal risk, which FN curve normally is said, like what frequency per year is required, acceptable region, alarm, unacceptable. Same the table is defined here. Like if here 1 raised to power -6, here is 1 raised to power -4, and below is a 1 raised to power -9 basically. That becomes under like fatality point of view, like how many fatalities we're expecting, then what should be the acceptable criteria. For example, if there could be 10 fatalities potentially, then probability or frequency or risk should be 10 raised to power -7 or below. It cannot be 10 raised to -5. It cannot be 10 raised to power -4. It's unacceptable. So this is understanding like how we accept the risk. Then if we make the contours like in the plant area, like a plant inner zone, the acceptance criteria is like a little lower, then higher and higher. Like here, plant, the fire could be there anyway. Then inner zone is 10 raised to power, like frequency wise, 10 raised to power -5. Middle zone 10 raised to power -6. Outer zone 10 raised to power -7. And unclassified zone, the risk should be basically is a location specific individual risk should be 10 raised to power -7. Now, just to make you awake, one more question. And you can see, okay. What is the main purpose of a hazard identification study in risk management? What is the main purpose of a hazard identification study in risk management? First option, to quantify the probability of failure of equipment, to identify potential hazard early in a project or operation, to calculate financial losses due to downtime, to avoid compliance with ISO 9001 standard. So the answer is coming. People are filling, mostly are right. Yes, gentlemen, ladies, please fill your number. Okay, good, mostly are right. It means people are participating, not sleeping. Okay, so this is the B. Identify potential hazards early in a project or in operation phase. Now, we also prepare FERA assumption register while doing study. There are like whatever data we are using, so we have to make an assumption register. That assumption register cover at least 12, not 12, maybe 23 activities. What are those 23 activities? One, like we have to hazard identification, which is done hazard workshop. Then isolatable section and failure cases, how we will be making those. This is a part of the assumption. The process parameters, like it may not be like 100% matching with the heat and material balance. Sometimes we have to adjust some numbers. Inventory assessment, we are doing those calculations, and those calculations has to be right and it should be recorded. Then isolatable sections and blowdown time, it has to be recorded, like we said in ESD 2 minutes or 5 minutes time. Parts count, how we are doing that, that should be part of the assumption register. Leak sizes and hole sizes distribution, as we will be using them. Failure frequency, how we'll be calculating. Then release direction and height of the elevation point of view on the plant. Then consequence model, consequence release height. Then averaging time, like a 0 minute, 5 minute, 10 minutes. Then we have a consequence modeling endpoint, human vulnerability, building vulnerability, occupancy and manning, like how many people are there in a particular time. Then area division risk ranking point, escape and evacuation risk, transport risk assessment, toxic zoning, tolerability criteria, sensitivity assessment, then metallurgical data. So these 23 things are made part of the assumption register, which would be part of the report. Then, like here, describe fire and explosion protection measure in the facility. For example, like what protection measures are there in the gas facility? For example, FNG system, then fire and gas like a detection system, whether it is linked with the shutdown or whether it would be only alert the alarm. If there is a automated delay system, fire suppression system, or there would be action by the operator. Then philosophy aligned with the facility like a response plan, like whatever modeling is being done, whether it's matching with the plant philosophy. Then fire protection system provided for different gas gathering areas. What kind of system is provided? So then fire and explosion protection measure adopted for gas gathering. Each area, how it is basically allocated, like area allocation, type of fire protection system, like whether we have normal hydrants, whether we have sprinkler system and dual system, like whether foam system is applicable. Then in the electrical installation or control rooms, what kind of like a CO2 system, FM 200 system, whatever system is being used, and whether it is automated or manual, all those aspects. Then portables and the support system, if there would be a like a movable vehicles for firefighting system, and those are also available within a nearby facility. Or we can also take some help for the nearby like civil defense system support as well. Like time to fail. For example, what time is applicable, like a steel plate, how much time in case of jet fire, poor flame or heat effect, these kind of asset can sustain, we should know. For example, steel plate under jet flame, only 5 minutes. After 5 minutes, steel plate may fail. Steel beam, 5 minutes. Jacket legs, 15 minutes. Riser pipe, riser process vessel, 5 minutes. In the jet fire, if a jet flame is affecting, pool flame is like 10 minutes, 10 minutes, 30, 10, and 120. Whereas if the radiation effect is coming 37.5 kilowatt per meter square, then 20, 60, 150, and 60. So these are the like, we know that this much time is available if any accident would occur, and that can affect these assets. Then there are like explosion is the consequence result of overpressure explosion effect on gas facilities are analyzed by considering the OGP 434-15 plant structure criteria as provided below. Like here, wood frame, trailer or shack, it can fail 0.07 bar if the pressure is caused by the explosion. Similarly, reinforced concrete or masonry shear wall building 0.28 bar pressure if caused by the overpressure. Then steel, concrete, and frame unreinforced masonry infill or cladding, this is the pressure bearing capacity, right? Like a complete frame may collapse if this pressure exceeds this number. So this one here, the second one, steel frame, metal sliding pre-engineering building, the acceptable pressure should be below 0.10, otherwise it can collapse. Then the identified sensitive receptors in gas facilities are assessed for important frequency as provided in the below table. For example, residential building, accommodation building, industrial buildings, non-industrial buildings, critical structures, escape, evacuation, rescue measures, HSE critical equipment and system. Here, like for fire and explosion, the acceptable criteria, impairment criteria is 10 raised to the power minus 6, 10 raised to the power minus 5, both are same. Similarly, for industrial building, 10 raised to the power minus 4, all within a large demonstration to 10 raised to the power minus 5, and 10 raised to the power minus 4 for explosion, and same a large demonstration up to 10 raised to the power minus 5. This is the criteria. Design accidental load impairment criteria. Then receptor identified for FERA study, like unit area, these numbers are changed. And then the critical receptors, like these are the structures, including the equipment and wellhead facilities. Then primary structure of pig receivers, slug catchers, and slug catcher and other tag numbers are there. then this tank, waste, then otherwise like a waste drum storage area, admin building, and those. So here, what we're trying to see, fire and explosion events can significantly impact facilities nearby, infrastructures, buildings, critical equipment, and escape and evacuation measures. Then FAIR identifies receptors for each unit with some receptors common across units to evaluate potential consequences. These are like more complication. As we do that, then in the practical working, it can give more sense. Then FERA modeling input, like when we are showing the software part a little bit, like uploading of raster image of project specific layout of the facility and surrounding areas. Number two, define process material as per a material composition of heat and material balance sheet for all the isolatable sections. Place marking of isolatable section in accordance with plant layout, locations, and activation of the fast safety specific model. Then parts count, failure frequency calculation, inventory calculation, as I said, also that information is provided as an input. Then update weather parameters as per actual site conditions. Here, then define risk marking and measuring reporting points on facility layout, raster image. Marking of buildings and other key installation around the facility along with population density data. Marking of potential explosion site on facility layout, drawing as per TNO games method and TNO color book methodology for congestion modeling. This also, when congestion is more, overpressure would be more. Then define risk effects levels in accordance with applicable risk input impact criteria. Then insertion of project specific ignition sources on the layout drawings raster image. So this way, the modeling in the software is done. Here, then next 10 and 11, 2 points are more, like other models, optimization actions as needed. Other model optimization action and it repeated. So it is also like we have to do some additional activities as we will be modeling the whole process plant into the like FERA software or SFETI software. Here, if you see this software overview, like we have routes, we have risk transactions, we got populations, buildings, multi-energy obstructions, BST obstructions, and so on, and boundaries and images. So it like this is the first screen of the SFETI software. Then next is we try to bring in the raster image of that plant with a specific scale. If scale is not particular, then it can show out of the proportion result. Here, like this is also data is changed. So, but we have to each isolatable section, there should be its all component and their composition, leading composition, which would be modeled into the software. Then all the potential like isolatable sections, placement, and their whole, what is applicable, all are marked one by one. It is a big work. This is like physical properties input, for example, for that each hole size, what the fluid is, the parameters for the process, temperature, composition, volume, mass, those are input. And then the rest of the calculation are taken care by the software. Then insertion of ignition sources. Like if there is an ignition source, potential like a heater or any hot spot or any vehicle or any aspect of electrical, that is substation or so, can be shown as a potential ignition sources in the facilities. Then marking risk ranking point receptors, like where we want to see that we have to mark those basically risk ranking points where we want to see the result. These are also risk ranking point, as you can see that there's blue dots which are marked into the facility as a sample. Then define consequence impact criteria. So we define that criteria into the model like as per the criteria defined earlier. These are the pool fire, jet fire, or flash fire. So and here final model when everything is ready before we run the calculation button. And if our full like a facility like a refinery or so, it can take days. But our smaller facility, this calculation run can take like a few hours. But for big facilities, it can take days because each isolatable section has to be calculated. And then first like a consequence part, then risk part, and then we see the all contours on the basically layout and the reports. Now there are FERA modeling outputs. So Miss Harim Rao would be presenting it because she's a practitioner, so she can present better than me. So she will present the FERA modeling output results, and then we will take the last question answers. That I will come back.
Okay, hi everyone. So over to the flammable gas dispersion assessment. So this assessment is typically carried out for 0.5 LFL and 1 or 100% LFL. So LFL essentially represents the minimum concentration of flammable gas in air that could ignite when in contact with potential ignition sources. And 50% LFL is typically the safety threshold by regulations, representing half the concentration required for ignition. So it shall be noted that within these flammable gas clouds, if they come into contact with ignition sources, fatalities may occur. So here, as we can see, this is the risk frequency contour for LFL, for flammable gas dispersion. So as we can see, some areas are more susceptible to flammable gas dispersion and flash fire than others. So areas, so we can see that within the purple and light blue contour, the risk for flash fire is a lot more significant and higher than in other areas within the facility. So I also wanted to point out that flash fire is predominantly are short duration events and have an effect on personnel, and hence shall be assessed in a greater level of detail in the quantitative risk assessment studies as opposed to FERA. Okay. Next to jet fire assessment. So as part of the thermal radiation assessment in FERA, we'll also be touching upon jet fire assessment. So the intensity level of interest for this case study is 37.5 kilowatts per meter squared. And this is assessed at a time of interest of 300 seconds. So 300 seconds essentially represents the time to failure for steel equipment. So as we can see, we have equipment that are potentially vulnerable to impact from jet fire 37.5 at a risk level of 1e to the power minus 5. And we've also performed a similar assessment for a risk level of 1e to the power minus 4. So here's the overall frequency risk level contours overlaid on the plot plan of the facility. So as anticipated, some areas of the facility are exposed to a higher level of risk than others. So in line with the DAL, design accidental load criteria for FERA, those areas of the plant which are exposed to a level of risk of at least 20 to the power minus 5, for those areas, risk reduction measures shall be brainstormed as this level is considered tolerable risk, and risk reduction measures shall be brainstormed. So some risk reduction measures which we would be looking at are PFP, passive fire protection, similarly AFP, by ensuring adequate active fire protection is made available in these areas. So similar to jet fire thermal radiation assessment, we also perform pool fire assessment if, as we can see, it's applicable to our case study. So the only difference between pool fire and jet fire assessment, the intensity level, although is the same, the time to failure is instead 600 seconds. So the time to failure identified for steel equipment that are potentially exposed to pool fire is identified to be 10 minutes, 600 seconds. So as we just discussed, those areas that are susceptible to pool fire impact at 1 to the power minus 4 or 1 to the power minus 5, PFP, passive fire protection, shall be recommendations for PFP shall be brainstormed and shall be implemented in line with API 2218. So next, over to vapor cloud explosion. So VCE occurs when a flammable gas or vapor mixture ignites in a confined or obstructed area, producing high velocity flames and significant overpressure. So typically, the TNO multi-energy model is utilized for VCE assessment. So low congestion has minimal impact, whereas high congestion increases overpressure with distant effects converging. So these are some of the PES or potential explosion sites that we have identified for our study as part of this case study. So for each of these PES, we further identify their dimensions, their area, and then we also identify the area or the volume of obstructions or obstacles within each PES. And accordingly, the VBR or the volume blockage ratio is determined. And then the curve number is determined in line with TNO Yellow Book. So the curve number takes into account several other factors as well, such as parallel plane confinement, the level of obstruction, etc. Further details are provided in TNO Yellow Book. So here, as you can see, these are the overall risk frequency contours for VCE. So these are further quantified in the form of exceedance curves, as we'll see on the next slide. So these exceedance curves essentially tell us the level of overpressure at a defined receptor. So for instance, if we look at the temporary refuge number 2, so for an overpressure level of 0.05, the associated level of risk is a little above 3e to the power minus 5. Sorry, next slide. So these exceedance graphs are further tabulated, as you can see. So, for instance, we've determined the level of overpressure at a risk frequency of 1e to the power minus 5 at identified critical receptors for the facility. And then we've also identified the impulse duration. So these impulse duration are essentially utilized in order to determine the blast overpressure requirements for these buildings that are exposed to 1e to the power minus 5 or 1e to the power minus 4 level of risk as an outcome of potential VCE. So next, over to escalation assessment. So we also carry out escalation assessment for potential jet flame impingement. So jet flame impingement is considered to occur for a heat flux of 250 kilowatt per meter squared in line with OGP. So we identify those equipment that could potentially get impinged by this level of heat flux or by jet flame, right? So as part of our case study, we haven't identified equipment that could potentially get impacted by flame impingement. So essentially, for those equipment that are identified, we usually carry out assessment for BLEVE or boil over, if applicable. So similar to jet fire escalation assessment, we also carry out pool fire escalation assessment. And as per our case study, as we can see, potential for escalation is negligible. So as we just discussed, potential failure events leading to escalation are identified using both consequence results as well as the site layouts. And equipment-specific barriers for prevention, detection, control, and mitigation are also reviewed, and recommendations are provided to reduce risk to levels as low as reasonably practicable. So next, over to fire zones. So fire zones are used to check whether a credible fire scenario from the facility have any adverse impact on the neighboring units area, resulting in potential escalation of the event. The intent of fire zoning is to ensure adequate separation distances are maintained between adjacent units, such that a credible fire should not escalate to the adjacent unit. So 3 criteria for determining fire zones are as follows. So thermal radiation of 12.5 kilowatt per meter squared at t is equal to 5 minutes. Thermal radiation at 32 kilowatts per meter squared at t is equal to 0 minutes, as well as explosion overpressure at 200 millibar for a risk level of 1e to the power minus 4. So this assessment is carried out for whichever case is determined to be governing. So as you can see here, the governing case appears to be 12.5 t is equal to 5 minutes. For jet fire, And for pool fire, again, it appears to be 12.5 at t is equal to 5 minutes. That appears to be the governing case for the fire zoning assessment. So based on this, we determine fire zones which the facility can be split into, and we also determine and we verify the fire water demand for each fire zone. Next, over to AFP review. So we also review the active fire protection for the facility. So we identify deluge valves. So in our case study, the OPP is equipped with standalone fire water systems with dedicated distribution to all fire zones, right? So automatic and remotely activated systems such as fire water, foam, clean agent, etc., are provided for all major fire hazards. Okay. So non-process buildings such use sprinklers, process areas, use clean agents and extinguishers. Tanks have foam systems. So these are some examples of AFP that were utilized in our case study. So it is not within the scope of FERA to essentially assess the vulnerability to AFP. These are assessed in a greater level of detail in the ESSA, which is the Emergency Survivability Assessment. So in the ESSA study, we identify vulnerability, redundancy, and fail-safe function for AFP systems, and we determine if this emergency system would be survivable in the event of an MAH.
We go to last part. Conclusion recommendations point of view. Basically, we identified the fire explosion risks, and we identified the risk levels at the receptors. Then accordingly, sensitivity cases were also run, and we looked at what kind of fireproofing, what kind of firefighting system, whether that is adequate or not. Those were the key findings. So we'll not go into those details here. And then there are some immediate recommendations and there were some long-term recommendations which have been given for the study. So leave that part because this is like a recommendation as we make. So now questions. Maybe before the few questions are there, like which of the following scenario picture represent a vapor cloud explosion? There was a slide before which was showing like 4 jet fire, flash fire, or explosion and dust explosion. So you have to identify which picture represent vapor cloud explosion. The answer is coming. So some right, some wrong. So it's there. It means not all right here, but mostly right. Some wrong are also there. The answer is C. If you see that here, first one is jet fire, then this is the direction of the pool fire, and this is a vapor cloud explosion. We cannot decide. This is just imagination, right? But it's a combination. Then practically, dust explosion was wrong, but the pool fire and the vapor cloud explosion, these pictures are nearby. Anyway, so next question. The result of FERA are mainly used. This other question. Reduce operational cost, ensure safe facility layout and specify fire protection requirement, improve employees' performance, design HVAC system. So the answer is being given by participant, mostly right. The answer is B, ensure safe facility layout and specify fire protection requirement. Maybe the last question before we go to the open question answer session. Which of the following parameters commonly used to evaluate thermal radiation impact from a fire? Which of the following parameters is commonly used to evaluate thermal radiation impact from a fire? Kilowatt per meter square, dB, which is and then degree C per minute, or kg per second. Mostly answer is right, and answer is kilowatt per meter square. So this takes us to the last part of the discussion. We still have a 5 minute. We can go 5 minutes more. And here all participants would be given a chance, if there's a question, to speak live and ask their question, and then I will try to answer as per my ability. So, Mr. Abdullah, Mr. Thomas, over to you. Loudly speak.
Okay. So, Mr. Muhammad Hassan Iqbal has asked, how do we link a relation between the FERA and HAZOP studies?
Let them give him a chance to speak.
So, Mr. Hassan, you have been given permission to unmute and
Yeah,
speak.
thank you
Please-
so much. Am I audible?
Yes, yes.
Yes.
Yeah, actually, as a matter of fact, I have two questions, but I'll keep it one for now. So regarding this study, you have actually given a great session. What is the difference between HAZOP and FERA? As per my understanding, I know this is yeah. Please continue.
See, HAZOP is a different technique which is called hazard probability assessment. And that study is done by a team of engineers, including mainly process and also supported by instrumentation, electrical and mechanical disciplines, where there's a HAZOP facilitator and scribes are there, and they use various guide words and try to see what unthinkable can happen on the facility. The main focus is on the operability of the facilities, the DCS, ESD, FNG, and operator's role. So HAZOP is entirely different study as compared to FERA. FERA is a fire and explosion risk assessment, which is done mainly by a software. So that's the difference. HAZOP is a workshop-based study, and FERA is a software-driven study. Okay, sir. Next question,
Thank you,
please.
Mr. Muhammad Hassan. So now on to Mr. Harun.
Can you open the question?
Hello, good afternoon. Can you hear me? Hello?
Yes, please.
Yeah, Mr. Harun,
Hello?
please ask.
Yes,
You're
yes.
audible, please ask.
Please, my question is like this. Where do we classify dust fire? You know, in the mining industry, we have, when there is too much accumulation of dust, maybe on the drilling machine or on the drilling bit,
See,
or in the
what
pit.
kind, see, when we do dust explosion assessment, right? Dust, there should be a reactive dust, right? See, as per NFPA 30, we know that like normal sand will not cause a dust explosion. There should be some explosive particles in the dust which may oxidize and may cause explosion. So it has to be seen, for example, in particular case what we are discussing, there is a sulfur dust in the sulfur handling unit, which may also get oxidized by oxygen and make sulfur dioxide. And in that oxidation process, there could be an explosion. So for dust explosion, there should be like flammable or oxidizable chemicals inside the dust. Then dust explosion will take place. Okay, sir.
Hello, am I audible?
Yes.
Yes, you are.
Yeah. Rao sir, first of all, thankful to you for such a wonderful session at all. And I have basically 2 to 3 questions related to each other. So I guess that you will answer it.
Yes, please go ahead. Go ahead, please.
Yeah. Yeah, first thing is that leakage rate or leakage hole. If we if we are on the contractor side or we are just providing the plant, we will take a small leakage for the HAZOPs and for the studies, safety studies that we conduct. So, what is the criteria? How we will convince the client that we have to take the 5 hole, 25 or the whole tube leakage hole? Second
See
question
here,
is,
as per first, but take this answer, then you could go to the next question.
yeah. Yeah,
So
please.
these hole sizes are selected as per TNO guideline. We are considering at least 4 hole sizes minimum. One is 5 hole. The result would be demonstrated along with the time. Second is 25 hole. Third is 100 hole. And fourth one is a full rupture or full bore hole, right? So it is not only one hole is being studied, and if in between client wish to add more hole sizes, that those hole sizes can also be added. So there is no limitation, but Generally, as per QRA guideline, which is called a purple book, the four hole sizes are there minimum.
Sir, basically my question is related to on which criteria we can select the 5 mm or the whole tube rupture.
No, no,
For
it's for,
example,
you see, that it is for every pipe or pressure vessel. Four minimum hole size are like there could be a minor leak, there could be a big leak, or there could be a more bigger leak, or there could be a full rupture. So all those four scenarios are modeled by the software. It is already built in.
so sir, we can take this guidelines for the HAZOP session as well. For example, the
No, no,
tube rupture
HAZOP is
case of
different. See, HAZOP different. There's no relationship. In HAZOP, we don't consider any leak. Why there
okay,
should
sir.
be a leak, first of all?
Okay,
HAZOP is
sir.
entirely different study. This is the
Okay, sir.
study like you see if there would be like pumps, like a double seal, there could be a hole that is considered as a 25 hole, which are quite big, but normally taken as a 5 hole, right? So, but in the
Yeah, yeah.
mechanical seal of the pump, that is normally considered for hazard area classification. But in general, like why there should be leak, first of all. If there would be a leak, then what could be a scenario? What dispersion, what kind of fire and explosion may take place? What would be the impact of toxic elements based on the volume in the facility that will lead to that particular disaster?
Sir, thanks. Thank you, sir. Sir, second one is LFL. We have taken 50%, but as far as the LFL concept is concerned, if the component having the LFL, for example, at 5 degrees C, so or or the composition is equivalent to LFL, then it may ignite. But during the slide, they have shown that 50% of the LFL they consider the ignition. So how it can be possible?
See, this is on the safe limit, basically conservative approach. So as like risk is like the situation could be kept within control. It's not like actual situation, it is a hypothetical situation. You can see that if there would be a leakage and when the like a flash fire or explosion will take place, because you are having a full dispersion taking place, there's a big volume of gas might be going out. So if the fire starts, then up to what extent it can go.
Thank you,
Sir,
Mr.
last
Kumar.
question. Sir,
Mhm.
sir, last question, please. Sir, my this is the generic one question. Uh, we have seen that in the places where a stringent safety studies will be conducted, like the refineries that you have shared the story that the incident happened in the first week of October. Even though stringent requirements in stringent work permit systems and the asset integrity systems and the risk-based inspection as well, but the incident occurred there a lot as far as
No, no, no.
we
Like,
compare with the
see,
third world countries.
no, no, no. Here, they are the victim of their overconfidence, right? And like, there is a one, since I'm from Pakistan, so we have a Urdu poetry. It is said that हादसा एकदम नहीं होता वक्त करता है परवरिश बरसों. This is a poetry. Like incident does not happen overnight. There are the causes which are accumulated over the time. So whenever there is a overconfidence, it can lead to an accident. Let's say Piper Alpha case. You can see that incident what happened like in Mexico, BP rig. There was an issue. There were like there's a movie available which showing that certain alarms were ignored. And Isomax, the unit which is a fire zone in the uh, this Chevron refinery, it is a known reactor which got exothermic reaction. It is required to be controlled. If anything fail on the cooling system side or any controlled parameter, there could be an accident. And it is not the only accident occurred. There are many other accidents occurred in the same unit. So the issues are there, but we need to manage. That's why we have to live day by day. And every moment, safety should not be considered granted. It has to be managed. Okay, sir.
Thank you, sir. Thank you. Thank you.
Thank you,
Thank
Mr. Nawab. Thank you.
Mr. Ashish Manchi Katla is the name.
Microphone resolution.
Okay, so this question is like, do we have FERA assumption register similar to FERA standard? Yes, this is the like as per the FERA standard. There is a requirement of assumption register for FERA. and that is prepared, covering 23 points. So thank you very much for your participation. I hope that this webinar was useful and it will help you for your growth in the career. Thank you very much. And we will be presenting next webinar after 4 weeks from now. Thank you and have a nice day.